All right, this is part two of section 4.3 dealing with what derivatives tell us. So in this video, I'm going to focus on concavity and inflection points. And then we'll also talk about the second derivative test. Now, the second derivative test can also be used for local extrema. That means local maximum and local minimum. Okay, I'll show you a few examples of those in this video. All right, let's talk about the concavity and inflection points. Here we're going to let f be differentiable on an open interval called I. If f prime is increasing on I, then f is going to be concave up on I. And if f prime is decreasing on I, then that means that your function will be concave down on I. And if f is continuous at C, and f changes concavity at C from up to down or from down to up, then that means that your function has an inflection point at C. Okay, that's the definition of concavity and the definition of an inflection point. And we're going to look at some illustrations of this. Let me go and give you this theorem for testing concavity. Let's say f prime of x exists on the open interval called I. If f double prime, or the second derivative of f, is positive on I, then that means that the function is going to be concave up on the interval I. Or if f double prime of that function, or the second derivative of that function, is less than 0 on I, then f is going to be concave down on I. And if C is a point on I in which f double prime changes sign at C, that means from positive to negative or vice versa, then your function f has an inflection point at C. And these are just some illustrations of where inflection points can, or you might not have an inflection point. So in these illustrations here, this first one does have an inflection point. As you can see, that is concave down, and then at C, to the left of it is concave down, to the right of it is concave up. And at C, that will be your point of inflection. Now here, your function f double prime of C does not exist. However, it is concave up to the left of C and concave down to the right of C. As you can see, here at C is changing concavity. These two do not change concavity. So at C is C right here. To the left of it is concave up. To the right of it is still concave up. At C here is concave down on the left, but still concave down on the right. So in this case here, point C would not be an inflection point because your concavity does not change. All right, so let's look at example 9 on the next page. Let's say we want to determine the intervals on which the following function is concave up or concave down and identify any inflection points. Okay. Let's say we got f of x is equal to 3x to the fourth minus 2x cubed plus 1. There are two things we need to identify, or we need to find. We need to find out what f prime of x is, and we need to find out what f double prime of x is. That's the first and the second derivative, okay? In order for you to get the second derivative, you must find the first derivative. So if f of x is equal to 3x to the fourth minus 2x cubed plus 1, then that means that f prime of x is this. The derivative of 3x to the fourth will be 12x cubed minus the derivative of 2x cubed will be 6x squared the derivative of 1 will be 0. Now we're going to take that to find our second derivative, which is, of course, the derivative of the first. So the derivative of 12x cubed would be, let's see, bring down the 3 multiplied by 12 would be 36. X to the 1 less power, that'll be 2, minus the derivative of 6x squared. We bring the 2 down, multiplied by 6, it'll be 12, copy the x over to the 1 less power. It'll be x to the 1, which is x. So f double prime of x will be 36 x squared minus 12x. Now we're going to set f double prime of x to be equal to 0. Now, f double prime of x was 36x squared minus 12x. So that's going to be set equal to 0. And now we're going to have to do some factoring here. The common factor that's in 36x squared and minus 12x will be 12x. So I factor out the 12x. 36x squared divided by 12x will be 3x. Minus 12x divided by itself will be 1. And then we set that expression to be equal to 0. So I'll have 12x is equal to 0. 3x minus 1 is equal to 0. We solve for x, so for the 12x is equal to 0, that means x is equal to 0. But 3x minus 1 is equal to 0, that means 3x is equal to 1. Divide both sides by 3, you'll get x is equal to 1/3. So these are my two possible points of inflection. X equals 0 and x is equal to 1/3. And I'm going to draw my number line. Now, in this case here, there is no interval given to us. So pretty much we're going to be dealing with everything from negative infinity to infinity. Let's see, I'm going to put 0 here. And then I'm going to put 1/3 over here. So now I got three intervals here. The first one will be from negative infinity up to 0. And then from 0 to 1/3. And then finally 1/3 to infinity. Then I'm going to pick test points in for each of those intervals to determine whether it's concave up or concave down. If f double prime of my value that I choose is positive, then that means it's going to be concave up. Or if f double prime of the value that I choose is negative, then that means it's going to be concave down for that interval. Starting with from negative infinity to 0, let's use -1. So f double prime of -1 would be this. I have to use my calculator for this one. Let me clear this out. Let's see, 36, and then left parentheses -1, close parentheses, and then square it. Minus 12 times -1, close parentheses. Here I get 48, and it's a positive 48. So that means f prime for negative infinity to 0, I'm going to get values for f prime of x that will be positive. So that means the graph will be concave up because f double prime was positive. Now for 0 to 1/3, I had to choose a fraction here like 1/4, because 1/4 is less than 1/3. And I'm going to find out what the sign is for f double prime of 1/4. So here I'm going to do 36, then left parentheses 1 divided by 4, close parentheses, and that's going to be squared. And then minus 12 times, and in parentheses 1 divided by 4. you'll get negative 0.75. Well, doesn't matter. It's going to be negative. That means between 0 and 1/3, I'm going to get values for f double prime of x that will be negative values. So that means that the graph of the function will be concave down. Concave down. And then finally, from 1/3 to infinity, I'm using 1. So f double prime of 1. Let's see, I know that's going to be 36, because if I square the 1, it's just going to be 1 times 36, which is 36. 12 times 1 will be 12. 36 minus 12 will be 24. That's going to end up being positive. So from 1/3 to infinity, I'm going to get values for f double prime of x that will be positive. So that means the graph will be concave up. Okay. So now let's check to see, in this case here, where our concavity changed. At 0, we went from concave up to concave down. That's a point of inflection. And for 1/3, we went from concave down to concave up. That's another point of inflection. Okay, so the intervals where it was concave up was from negative infinity to 0, as you can see, and then again from 1/3 to infinity. And then it was concave down only from between 0 and 1/3. So the points 0 and 1/3, those two are the points of inflection. Because at those two x values, the concavity changed. X equals 0, we went from concave up to concave down. And then at x equal 1/3, we went from concave down to concave up. Okay. All right, let's look at another example. Let's say I want to determine the intervals on which the following function is concave up or concave down. Identify any inflection points. Here we got f of x is equal to 5x to the 4th minus 10x cubed minus 15. In this case, we got to first take the first derivative and the second derivative. The derivative, or the first derivative of 5x to the 4th minus 10x cubed minus 15. Well, for 5x to the 4th, we bring the 4 down, multiply by 5, that'll be 20. X to the 3rd minus, bring the 3 down, multiply by 10, it'll be 30. X to the 2nd. So I got 20x cubed minus 30x squared. That's the first derivative. Now for the second derivative, I take the derivative of the first derivative. So 20x cubed, its derivative will be 60x squared minus, for 30x squared, its derivative will just be 60x. So f double prime of x will be 60x squared minus 60x. And then we go ahead and set f prime of x to be f double prime of x to be equal to 0. So that means this will be 60x squared minus 60x equal to 0. And let's factor out the left side. The common factor in 60x squared and minus 60x will be 60x. And then 60x squared divided by 60x will be x, minus 60x divided by itself will be 1. Now we're going to set each factor equal to 0. So that means I have 60x is equal to 0 and x minus 1 is equal to 0. Well, for 60x is equal to 0, that means x is equal to 0. And for x minus 1 is equal to 0, that means x is equal to 1. So x equals 0 and x equals 1 are my possible points of inflection. Okay, we're going to find out. I'm going to put 0 here. And I'll put 1 over here. And there is no set interval given to us, so we're going to say for this first interval, negative infinity to 0. The next one will be from 0 to 1. And the last one will be from 1 to infinity. I'm going to use these to determine whether my graph is going to be concave up or concave down on each of those intervals here. So from negative infinity to 0, I'm going to use negative 1. And I'm going to evaluate f double prime of negative 1. And this I can do pretty much do in my head here. Negative 1 squared would be positive 1, so this is going to be 60 here. Minus 60 times a negative 1 would be plus 60. So 60 plus 60 will be 120. That's going to end up being positive. So from negative infinity to infinity, I'm going to get positive values for f double prime of x. That means the graph of the function will be concave up. Now between 0 and 1, I have to say 1/2. I know that's kind of iffy, but we're going to use 1/2 and then substitute 1/2 in this f double prime of x. So here's the calculator. I'm going to do it here. Let's see, 60 left parentheses, 1 divided by 2 close parentheses, and then square it, minus 60 left parentheses, 1 divided by 2 close parentheses. Here I end up with negative 15. And it's negative, so that means between 0 and 1, I'm going to get values for f double prime of x that will be negative. Okay, so that means that the graph of the function is going to be concave down. That's because I came up with a negative for f prime of x. And now for 1 to infinity, I'll use 2 as a test value. So f double prime of 2, if I do this in my head, now if you want to, you can do this in the calculator. 2 squared is 4 times 60 is 240. This is 60 times 2, that's 120. So 240 minus 120, that's going to give me a positive number. So that means that f double prime of 2, for 1 to infinity, my second derivative values will be positive. So that means that the graph of the function will be concave up. So now I can identify the intervals where this function will be concave up. So by looking at this, it's going to be concave up on the intervals negative infinity to 0 and concave up again from 1 to infinity. And concave down, well, it's only going to be concave down between 0 and 1. And my points of inflection, they of course have to change concavity. At 0, it changes concavity. I'm going from concave up to concave down. And at 1, that's another point of inflection. I'm going from concave down to concave up. So x equals 0 and x equals 1 are my 2 points of inflection. Okay. All right, let's look at one more of these, and then we'll go into the second derivative test. Let's say I want to determine the intervals on which the following function is concave up or concave down. Identify any inflection points. And here I got, in this case, f of x is equal to negative of the natural log of 2x squared plus 7. Now let's find the first derivative here, f prime of x. And it's going to be negative. With this, we have to apply the chain rule. And also, the derivative of the natural log of anything would be 1 over whatever that is times its inside derivative. So the derivative of negative, I'm bringing down the negative, the derivative of ln of 2x squared plus 7 will be 1 over 2x squared plus 7. And then that's multiplied by the inside derivative. The derivative of 2x squared plus 7 will be 4x. Okay. So in this case here, f prime of x will be negative 4x over 2x squared plus 7. And of course, I'll leave that as is. Now we need to take the second derivative of our first derivative. For this time, we have to use the product rule, as I have a numerator and a denominator. And of course, if you remember, the product rule is this. We take our denominator, which is 2x squared plus 7, times the derivative of the numerator. The derivative of negative 4x will be negative 4. And then minus the numerator, which is minus 4x, times the derivative of the denominator. 2x squared plus 7, its derivative will be 4x. All that's divided by the square of the denominator. 2x squared plus 7, and that's going to be squared. Now let's simplify the numerator the best way we can. So here f double prime of x will be, if I distribute the negative 4 of the 2x squared plus 7, this will be minus 8x squared minus 28. Negative 4 times the 2x squared will be negative 8x squared. Negative 4 times the plus 7 will be minus 28. Now, minus a negative will be a plus. 4x times 4x will be 16x squared. All divided by the quantity 2x squared plus 7, and that's going to be squared. Now, if I combine like terms in that numerator, I have f double prime of x will be 16x squared minus 8x squared will be 8x squared minus 28 divided by the 2x squared plus 7 quantity squared. Y'all excuse me, let me make that double prime look like a double prime. Okay. So that's what f double prime of x will be equal to. 8x squared minus 28 divided by 2x squared plus 7 quantity squared. All right, so now we're going to set f double prime of x to be equal to 0. And notice we got a rational function here. 8x squared minus 28 divided by the quantity 2x squared plus 7 quantity squared. That's going to be set equal to 0. So with a rational function, we set the numerator to be equal to 0 and the denominator to be equal to 0. And then we simplify. So for the 8x squared minus 28 equal to 0, if I add 28 to both sides, that would mean 8x squared is equal to 28. Divide both sides by 8. This will be x squared is equal to, if I reduce 28 over 8 in its simplest form, by dividing the numerator and the denominator by 4, I would get 7 over 2. And then take the square root on both sides. And I have to include that plus or minus symbol. This will be x is equal to plus or minus. I'm going to break that up as the square root of 7 over the square root of 2, and then rationalize the denominator by dividing the numerator and the denominator by 2. So that means x is equal to plus or minus the square root of 7 times the square root of 2 will be the square root of 14 divided by the square root of 2 times itself. It wipes out the radical. So I have a 2 in the denominator. So x then will be equal to plus or minus the square root of 14 over 2. And now for the 2x squared plus 7 is equal to 0. Well, and this should be quantity squared. Sorry, that should be quantity squared from that denominator. Well, I'm squaring the whole thing. So if I take the square root on both sides of this, and I don't need that plus or minus because I'm taking the square root of 0, which is 0. And 0 is neither positive nor negative. But that wipes out that square, so it'll be 2x squared plus 7 equal to 0. Subtract 7, you'll get 2x squared is equal to negative 7. Divide both sides by 2. This will be x squared is equal to negative 7 halves. But if I take the square root on both sides, of course, I need the plus or minus, by the way. Notice I can't take the square root of a negative number at all. So that means I can cross all that out because I'm going to get a pair of imaginary numbers, and I'm not going to be able to deal with a pair of imaginary numbers on a graph. So that means your only possible points of inflection will be x is equal to the square root of 14 over 2, and x is equal to negative square root of 14 over 2. Okay. Now, I'm going to have to bring this down a bit because I need my number line. There's a lot going on in this problem. All right, so I'm going to say negative square root of 14 over 2 is going to be here, and positive square root of 14 over 2 will be over here. So my intervals will be from negative infinity up to negative square root of 14 over 2. Then from negative square root of 14 over 2 to positive square root of 14 over 2. Then the last one will be square root of 14 over 2 to infinity. Let's see here. I had to pick test values here. And by the way, these are my possible points of inflection. That's going to help me determine whether they are concave up, which intervals are concave up and which ones are concave down. All right, for negative infinity up to negative square root of 14 over 2. Now here I pick negative 2. And the reason for that is this. If I do negative square root of 14, divide that by 2, that number would be like negative 1.87, and negative 2 would be in that interval. So we can use negative 2 there. And then I'm going to do f double prime of negative 2. Now I'm going to use this up here, that 8x squared minus 28 divided by 2x squared plus 7 quantity squared. let's see, square root of negative, that's going to be positive. So 2 squared would be 4 times 8 would be 32. 32 minus 28 would be 4. That's going to be positive. This denominator is automatically going to be positive. So positive divided by a positive will give me a positive number. And that means from negative infinity to negative square root of 14 over 2, those values for f double prime of x will be positive. So that means the graph will be concave up. And now for negative square root of 14 over 2 to positive square root of 14 over 2. Let's use 0. Because I have a negative on the left and a positive on the right. That means 0 is in between those two. Then we do f double prime of 0. Looking at this here, if this is going to be 0, this 0 minus 28, that's going to be a negative number. The denominator will automatically be positive. So negative divided by a positive would end up being negative. So that means between these two numbers, f double prime will be negative. That means the graph of the function will be concave down. Concave down. And then finally, the square root of 14 over 2. I know that's going to be a positive 1.87 up to infinity. Let's use a positive 2. And then find f double prime of 2. All right, in this case here, 2 squared will be 4 times 8 will be 32, minus 28 will be a positive number. In the numerator, the denominator will always be positive for this case, in this case. So positive divided by positive will be a positive. So for f double prime on that interval, I'll get positive values for f double prime of x. The graph will be concave up. So now, as you can see, it's going to be concave up on these intervals from negative infinity up to negative square root of 14 over 2, and also concave up again from the square root of 14 over 2 to positive infinity. And then concave down only between negative square root of 14 over 2 to positive square root of 14 over 2. And your points of inflection. Of course, your concavity has to change in order for it to be a point of inflection. All right, so for negative square root of 14 over 2, we went from concave up to concave down. That would be a point of inflection. And then for positive square root of 14 over 2, we went from concave down to concave up. So square root of 14 over 2 is your other point of inflection. Okay. All right, let's look at the next example. In this case, we have, so here we're going to determine the intervals in which the following function is concave up or concave down. Identify any points of inflection or inflection points, doesn't matter which one, how you say it. Okay, let me try to zoom in a bit. There we go. Here we got f of x is equal to 2x to the fourth plus 8x cubed plus 12x squared minus 24x minus 8. In this case here, we're going to find f prime of x and then f double prime of x. For 2x to the fourth, that derivative will be 8x cubed plus the derivative of 8x cubed is 24x squared And then for 12x squared, that will be plus 24x. And then minus the derivative of 24x will be 24. And of course, the derivative of 8 would be 0. And now we're going to find f double prime of x. F double prime of x. Taking that derivative, the derivative of 8x cubed would be 24x squared. Plus the derivative of 24x squared would be 48x. Plus the derivative of 24x will be 24. So here we got f prime of x equaling to 24x squared plus 48x plus 24. And now we're going to set f double prime of x to be equal to 0. So that means I have 24x squared plus 48x plus 24. That's going to be set equal to 0. Now let's find a common factor that's in 24x squared, 48x, and 24. That's obviously going to be 24. So if I factor out the 24, this will be x squared plus 2x plus 1. That's equal to 0. And if I factor x squared plus 2x plus 1 into two binomials, let's see, x squared breaks up as x and x. Factors of 1 that give me 2x will be plus 1 and another plus 1. And since x plus 1 is used as a factor twice, I can say 24 times the quantity x plus 1 squared is equal to 0. And then solve this equation for x. So if I divide both sides by 24, I'm going to get x plus 1 quantity squared is equal to 0. And then take the square root on both sides. So that means x plus 1 is equal to 0. That would mean x is equal to negative 1. So the only possible point of inflection would be x equal negative 1. And I say possible point of inflection. So if I draw my number line, so then negative 1 breaks it up into two intervals here, from negative infinity to negative 1, and then from 1 to infinity, because that's going to help me determine my possible concavity here. So for negative infinity to negative 1, this should have negative 1 here. Negative infinity to negative 1, let's use negative 2. And do f double prime of negative 2. So this will be 24, and then negative 2 in parentheses, and then that's squared, plus 48, negative 2 in parentheses, plus 24. Here I came up with a positive value there. So at f of negative 2, it was positive. So from negative infinity to negative 1, all of the values for f double prime of x will be positive. So the graph will be concave up. And now for negative 1 to infinity, let's use 0. Now let's do f double prime of 0. Well, this is going to be 0. That would be 0. I'll be left with 24, and it's positive. So that means from negative 1 to infinity, f double prime, the values for f double prime of x will be positive as well. So that graph on that interval will be concave up as well. So notice the graph did not change concavity. So that means that there is no point of inflection, because I'm going to be concave up all the way through from negative infinity to infinity. So concave up would be from negative infinity to positive infinity. And points of inflection, there are none. Because I did not change concavity. Okay. All right, now let's look at our second derivative test. And this helps us identify local maxima and local minima. In the last video, we did the first derivative test to help us find our local max and local min. Here we can use the second derivative test to do that as well. All right, so this right here is a short step to a test that uses a second derivative to identify local maxima and local minima. So here's the theorem. Suppose that f double prime is continuous on an open interval containing C with f prime of C equaling to 0. So here, if f double prime of C is positive, then that means the function will have a local minimum at C. If f double prime of C is less than 0, or if it's negative, that means that f has a local maximum at C. And if f double prime of C is equal to 0, then the test will be inconclusive. So that means that f may have a local maximum or local minimum or neither. Okay. So when your second derivative ends up being equal to 0, then that means the test fails. It's going to be inconclusive. Okay. Now, if you look on the next page, you'll see illustrations of that. Okay. F prime of C was 0, f double prime of C became positive. So there is a local minimum here. And on the right is your local max, where f double prime of C was negative and f prime of C was 0. Now let's look at this example. Locate the critical points on the following function and then use the second derivative test to determine whether they correspond to a local maxima, local minima, or neither. And in this case, we got f of x is equal to negative x cubed plus 3x squared. So in this case here, we need to take the first derivative to find out what our critical points are going to be. So we do f prime of x. The derivative of negative x cubed would be negative 3x squared, plus the derivative of 3x squared would be 6x. And then we set f prime of x to be equal to 0. And the first derivative was negative 3x squared plus 6x equal to 0. Now let's factor out the negative 3x. That would mean negative 3x squared divided by 3x will be x. 6x divided by negative 3x will be minus 2. So I got negative 3x times the quantity x minus 2 equal to 0. And then we set each factor equal to 0. So that means negative 3x equals 0. X minus 2 is equal to 0. And each equation will solve for x. So for negative 3x is equal to 0, that means x is equal to 0. X minus 2 equals 0 means x is equal to 2. So these are my critical points. And that's all they're asking for here. Well, part of what they're asking for is just the critical points. X equals 0 and x is equal to 2. Okay, now we're going to use a second derivative test to determine whether they correspond to a local maxima or local minima, or neither. This is where we take the second derivative. We look at f prime of x, which is negative 3x plus 6x. So its derivative will be, let's see, negative 6x plus 6. Okay. Now we're going to substitute our critical points into f double prime of x. So we're going to find f double prime of 0 and f double prime of 2. Let's start with f double prime of 0. Here we're going to have negative 6 times 0 plus 6. Well, negative 6 times 0 is 0 plus 6 will end up being 6. And it is positive. And then for f double prime of 2, this will be negative 6 times 2 plus 6. Well, negative 6 times 2 is negative 12. Negative 12 plus 6 will be negative 6. And it ends up being negative. Okay. So we need our local minimum and local maximum. LO. And it does tell us that if the f double prime of c is positive, that means we have a local minimum. Here's positive for f of 0. So at 0, we have a local minimum. So at x equals 0, we have a local minimum because we came up with a positive value. And if it's negative, that means we have a local maximum. Negative here means at 2, x equals 2, we have a local maximum. Okay, that's all there is to it. Okay. All right, let's try this next example here. Let's say we get f of x is equal to negative 3 minus 4x squared. And we're going to locate our critical points for that function and then use the second derivative test to determine whether they correspond to local maxima or local minima or neither. All right, let's find out what f prime of x is going to be. The derivative of negative 3 is 0. The derivative of minus 4x squared will be a minus 8x. So f prime of x will be negative 8x. And then we're going to set that function f prime of x to be equal to 0. So it'll be negative 8x equal to 0. That will have to mean x is equal to 0. So here, that critical point would be at x is equal to 0. Now we're going to find f double prime of x. Well, if f prime of x is negative 8x, that means that f double prime would mean the derivative of negative 8x would just be negative 8. Okay. The only critical point we have is at 0, so we're going to find f double prime of 0. Well, that's easy. Since f double prime of x is negative 8, that means that f double prime of 0 has to be negative 8. Negative 8. And of course, it is negative. That tells me that I have a local maximum because f double prime at 0 came out to be a negative number. So my local maximum was that x is equal to 0 for the local minimum. There is none. Okay. All right. All right, let's try this next example here. All right, let's say we got f of x is equal to e to the x times the quantity x plus 4. And I want to locate the critical points for that function and then use the second derivative test to determine whether they correspond to a local maxima, local minima, or none, or neither. So for f of x equal to e to the x times x plus 4, if I want that derivative, I will have to apply the product rule because I have e to the x times the x plus 4. And the product rule is this: I take the first, which is e to the x, times the derivative of x plus 4, that's simply going to be a 1, plus the second, which is x plus 4, times the derivative of the first. The derivative of e to the x is the easiest derivative to take. It will be e to the x. And now let's simplify this a bit. E to the x times 1 is e to the x. If I distribute, actually, well, let me go ahead and bring this down. And then I can factor e to the x out. Probably be the easier way to do it like that. If I factor out e to the x divided by itself will be 1, plus this divided by e to the x. I factor out the e to the x, I'll be left with x plus 4. And then I can combine like terms here. 1 plus 4 would be 5. So it'll be e to the x times x plus 5. Okay, so that's the derivative there. And now we're going to take f prime of x, set that equal to 0. So I got e to the x times the quantity x plus 5, and that's going to be equal to 0. And then we set each factor equal to 0, so that'll be e to the x equal to 0, and then x plus 5 is equal to 0. Now for e to the x equal to 0, if I try to take the natural log on both sides, that's not going to work because I'm not going to be able to take the natural log of 0 at all. Now I can simplify ln of e to the x because ln of e to whatever will be whatever. So it'll be x equal ln of 0, but I have to get rid of that because the natural log of 0 does not exist. But I can solve the x plus 5 equal to 0. That will give me x is equal to negative 5. Okay, so that's my critical point. So my critical point there would be x is equal to 5. I mean, x equal negative 5. X equal negative 5 is my critical point. All right, now I need f double prime of x. This is what f prime of x is, e to the x times the quantity x plus 5. Again, I have to use the product rule. And that's this. The first, which is e to the x, times the derivative of x plus 5, that's going to be 1, plus the second, which is x plus 5, times the derivative of e to the x, which is e to the x. And I might as well go ahead and factor out e to the x. So if I do that, I'll have a 1 plus the x plus 5. And combine 1 and 5 together, that will be 6. So it'll be e to the x times x plus 6. So that's what f double prime of x is. Now I substitute the x with my critical value of x is equal to negative 5. So here I'm going to have e to the negative 5 times negative 5 plus 6. Let's see, bring down e to the negative 5, add negative 5 and 6 together, you'll get 1. 1 times e to the negative 5 would be e to the negative 5. And that's going to end up being, if you take that as a decimal, let's see, second ln for the e, and then negative 5. I'm going to get a positive value. And this is going to be that answer to 3 decimal places, 0.007, which is positive. Okay. So when it's positive, that tells me I have a local minimum. So in this case here, I can say the local minimum will be at x equal negative 5. And I don't have a local maximum. Because I don't have a negative x, I don't have a negative value for f double prime of x. Okay. All right, and finally, same thing, but here we got f of x equal negative 2x cubed minus 12x squared plus 7. And we want our critical points, and then using that second derivative test, we want to determine whether they correspond to a local maxima, local minima, or neither. Okay, so let's take the derivative of this function, f of x equal to negative 12x cubed minus 12x squared plus 7. So f prime of x will be, the derivative of negative 2x cubed will be a negative 6x squared. The derivative of minus 12x will be a minus 24x. The derivative of 7 is 0. And now let's set f prime of x to be equal to 0. That helps us find our critical points. So I get negative 6x squared minus 24x equal to 0. Well, let's see if we can factor out the negative 6 in this problem. Negative 6x squared divided by negative 6x will be x. And this will be plus because the minus times the minus divided by a minus will be a plus. 24x divided by 6x will be 4. And that's equal to 0. And then we set each factor equal to 0. So that means negative 6x equals 0 and x plus 4 is equal to 0. And then we solve for x for each equation. So for negative 6x equals 0 means x is equal to 0. For x plus 4 equal to 0, that means x is equal to negative 4. So these are my two critical points here. Or critical values, I should say. X equals 0 and x is equal to negative 4. Because points have an x and a y coordinate. And I'm only giving you the x value as they ask for in the homework. And now I'm going to find my second derivative here, f double prime of x. If this is my f prime of x, then the derivative of negative 6x squared will be negative 12x minus the derivative of 24x will be 24. And then we're going to find f double prime of 0 and f double prime of negative 4 using this. So at 0, I'm going to have negative 12 times 0 minus 24. And this is going to end up being negative 24. So it's negative. So that tells me I have a local maximum. And that's that x is equal to 0, because at 0, I came up with a negative value. Now for f double prime of -4, this will be -12 times -4 minus 24. Well, -12 times a -4 will be 48. 48 minus 24 is 24. And that is a positive value. So that tells me I'm going to have a local minimum at x equal -4. Okay. Okay. Now on the final page is just a recap of the derivative properties here. So we looked at a lot of stuff here that deal with the first and second derivative of functions that provide valuable information about its graph. So in this case here, if a function is differentiable on an interval, that means you're going to have a smooth continuous curve like this, as you can see here. If f prime, the first derivative, is positive on an open interval, that means it's going to be increasing on that interval, as you can see. Or if f prime is negative on an open interval, it's going to be decreasing on that interval. And then we talked about changing sign. Of course, if we increase and then decrease, that means you have a local maximum. Or if you decrease and then increase, that means you got a local minimum. Okay. Now, in this case here, if f prime, the first derivative, is equal to 0, and I know that's hard to see, but that's equal to 0. But f double prime is negative, that means you got a local maximum. Or if f prime is equal to 0 and f double prime is positive, that means you got a local maximum. And then these last three deal with concave up. If f double prime is positive on the open interval, it's concave up. Or if f double prime is less than 0, or if it's negative on the open interval, that means your graph will be concave down. And then, of course, the inflection point is when you have a change in concavity. That means your second derivative goes through a change in sign from positive to negative, or from negative to positive. Okay, so that's just pretty much a recap, pretty much what section 4.3 was all about. And that does finally conclude section 4.3, dealing with what derivatives tell us. I realize that it takes like 2 parts in order to complete this particular video, but if you go through this as much as you can, you should be able to conquer the homework for this section. Feel free to contact me if you have any questions about the problems that are in the homework from MyMathLab, or any questions about the problems that are presented in this video.